Hello everyone, welcome to Basic Chemistry Plus. Today we are going to talk about the DNA block atomic radii. Before that, I want you to go through the description. I am putting the link of the first video where I have talked about the electronic configurations over there. So first we would be moving on to the atomic radii, and I like to focus on the graph over there to show you how it works. Over here, you can see that from scandium to chromium, the curve decreases, which is something supposed to happen as you move from left to right. But there, chromium to cobalt and nickel to zinc, you can see that's something abnormal. Chromium to cobalt, it's just a straight line, and nickel to zinc, it's an increasing. So like chromium to cobalt, they have same value. If you look into the next transition series, and next to next transition series. So right now I'm showing you the third transition series, how it looks like. So there we have gold over here, and here we have mercury. Yeah, now this is our hafnium. Zirconium and hafnium fall into the same point. Niobium and tantalum as well falls into the same point, and silver and golds are also in the same point, but mercury and cadmium has some difference. Now try to understand. Say first, zirconium and hafnium, although they are in two different groups, they have same value. Niobium and tantalum, different groups, same value. And gold and silver, they have also different groups but same value. So this is not something which is supposed to happen, isn't it? So let's find out why is it happening. Okay, that is not happening for the first and the second transition element. Over there you can see there is a big gap, but not in here. Here the second and the third transition series is same because of the decontraction. The reason behind it is decontraction. Okay, now what is decontraction? D is an orbital having poor shielding effect. You know that from class 11 in organic chemistry. Now what do we mean by poor shielding? So shielding is something, let's write an equation. Z star equals to Z minus S. Remember this equation where Z star is the effective nuclear charge, Z is the nuclear charge, minus S is the screening constant. So what is screening? Let's say there is nucleus having Z amount of nuclear charge, and let's say there is an electron over here. Now this electron, which is supposed to get the Z amount of attraction power, it won't get the same. It would get something lesser than that because of the inner orbital would shield some of the power, and the power which would be coming to electron, that's called Z star. So Z star is nothing but the reduced nuclear power, reduced or effective nuclear charge. Okay, so S is the amount by which the nuclear charge got shielded, okay, or screened over here. Now let me show you how is it affecting the atomic radii. Now when you're moving from scandium to vanadium, chromium, the value is decreasing, which is completely understandable, which is what happens when you move from left to right in a periodic table. So radius would decrease, okay, because of the higher nuclear charge when you move from left to right. But over here, the radius decreases more than the S block element because of the lanthanide contraction or decontraction. They are just the same, D and F. Okay, decontraction and F contraction is called lanthanide contraction. I'm going to talk about that. So first, let's understand what is it. From molybdenum to nickel, manganese to nickel, they have same radius. They have same atomic radius. So first part is clear to us. This would decrease. Okay, but why the radius is same over here? Now the reason behind it is, one, there are two factors which are working against each other. One is nuclear charge, which is trying to synchronize the atom, which is known as Z star, okay, which is trying to attract the electron. And second thing is interelectronic repulsion. So nuclear charge is trying to decrease the size of the atom, and interelectronic repulsion is working against it. Now let's understand how is it working against it. So if I draw a shell over here, this is the nucleus and this is the orbits. So let's say there is an electron over here. Okay, now this electron is being attracted by the nucleus by the effective nuclear charge, and as a result the electron would try to come closer to the nucleus, so the size of the atom would decrease. Okay, so nuclear charge is trying to close up the atom. But when they are trying to come near each other, there are electrons in the other shells as well. Now these electrons would repel this electron. As a result, there would be an interelectronic repulsion. So interelectronic repulsion won't let them come closer, right? and nuclear charge would try to let them come closer. So actually interelectronic repulsion and the nuclear charge, both of them are exactly the same over here. That's why it is neither decreasing nor increasing. Now if you just have a look on the last part, from the copper to zinc, over there you'll be able to see it is increasing. So use your common sense now. Why is it increasing? It is not decreasing. Why is it increasing? So definitely here the nuclear charge is lesser. Okay, it happens in all of them. So why is it increasing over here? Because definitely the interelectronic repulsion is now winning over the nuclear charge, because interelectronic repulsion is a repulsive force and nuclear charge is an attractive force. So definitely that's more repulsive force is more, that's why they are going out. So this is seen in D8, D9 and D10 electronic configurations. Okay, so over here as well you can see the same thing in ZnCd8G. So in a nutshell, the nuclear charge is trying to shrink the atoms, trying to decrease the radius. Interelectronic repulsion is working against it. It is trying to expand the radius. So that is why together they are showing these type of properties, right? So now I would be talking about why zirconium and hafnium, now niobium and tantalum, although they are from two different groups, they have two different groups, means the same group but two different periods, right? Still they are showing the similar value, the exactly same value. So why is this happening? Okay, now when you're moving from one group to another group, one period to another period, what happens is the over here, let's say titanium is 3D, zirconium is 4D and hafnium is 5D. The last shell is 5D. So one shell is increasing. So as the shell increases, the size should increase, right? But that's not happening, because over here we have lanthanum. So after zirconium we have lanthanum. Check the periodic table. Now zirconium and hafnium, in between them we have lanthanum, and lanthanum shows lanthanoid contraction or F block contraction, because lanthanoids contains F block. They are called F block elements, F orbitals. Now the shielding effect trend goes like, tuning effect trend goes like S, then P, then D, then F, right? The screening power is S, P, D, and F. So F over here contains the lowest screening power, means the S value is the lowest over here. Now think about the equation again. When you are moving from 4D to 5D, the Z star would be equals to Z minus S. Now S is very low for F block elements, for lanthanoids. That's why it is very low, almost negligible. So as a result, Z star and Z would be just the same. So the nuclear charge is very much effective over here. That is dominant over here. As a result, the synchronization is happening more. So as a result, although they are having two different orbits, same goes for niobium and tantalum as well. Although they are having two different orbits, still they would be showing same value. Same goes for gold and copper as well, gold and silver as well. Okay, so that's why this happens. This is a very important topic that we have done. Okay, over here you can see this is our trend for the ionic radii. That shows a similar trend over here. Just the values are given over here. Now we'll be moving on to the density. Okay, density is mass by volume. You do understand that. Now let's see what would happen. So the first point over here is that atomic volume of transition elements are low compared with S block. I have told you this. Look, mass by volume, right? Atomic volume of transition elements are lower. Now why is it lower? Because of the decontraction, the sizes are lower. That's why. So the density is comparatively high. So remember always, D block elements have very high density. Okay. Why the atomic volume is lower? I told you, lanthanoid contraction. You should rather say it, decontraction. Okay. You can better write it decontraction, or you can write lanthanoid contraction as well. Okay. Lanthanide contraction is mainly visible in after lanthanum. Okay. So you can write it decontraction. So density is comparatively high because of the contraction, because size decreases more, but mass is increasing anyway. Osmium and iridium has highest density in this transition elements, and this is important. Remember these two names. In all the groups, there is a normal increase in density from 3D to 4D series. Why is that? For 4D to 5D, and increase in due to lanthanoid contraction example. Now let's just try to understand what are they trying to say. Over here, look into it. Zirconium and hafnium and titanium. Zirconium has very low value than hafnium, but zirconium has same value with hafnium with respect to radius. But the mass of hafnium is very more than zirconium, na? So as a result, M by V, if you just think about mass by volume, mass is increasing but volume remains same. Mass is increasing but volume remains just the same. So definitely for hafnium, the density value would increase tremendously. This is understandable, right? Now, in 3D series, from scandium to chromium, it is decreasing. So from the volume is decreasing. Okay, density is decreasing because the volume is decreasing. Now, why the volume is decreasing? From scandium to chromium, you know that over here the radius decreases, right? From manganese to nickel, the radius remains same. So volume would remain same as well. So volume is constant. And on the last part here, the radius increases, so volume would increase. That's why you can see the reverse order is followed by the density. Okay, volume and density are reversed. Copper has highest and AC has lowest density of D block. Okay, first D element, transition element. Okay, now copper has highest and scandium has lowest. Now, why is it lowest? Because of the low volume. Okay, okay, it would be high volume, not low volume. Scandium has very high volume because of that. Okay, just check it, just correct it. It would be high volume. Okay, I'm not writing it anymore. So the density order now, this is very important, guys. See, iron, nickel, and copper over here. See, iron and nickel. Nickel is having greater density than iron, which is understandable because nickel has um, very higher masses than iron, isn't it? Mass of nickel is higher than iron. But if you see nickel and copper, and over here there are two more trends. So let me just show the diagram. It will be better for you to understand. So this is how it looks like, isn't it? This is how the D block size looks like. Over here, this is 3D. Okay, so 3D means first transition element. So this will be nickel, and over here will be copper. So you might be thinking copper has more radius, so more volume, so density would should decrease, right? But the copper's mass is very high. Because of that, the density is higher than nickel. That's why we need to know this trend. If you move on to the next one, over here you can see iron, copper, and Au. So let's draw its diagram as well. Let's find out where are they. So copper, just a second. So if I write it, it would be like copper, Ag, Au, right? This is 3D, 4D, and 5D. But Ag and Au have same size, isn't it? Remember, we have talked about this. Let's say this is the curve for Ag. If I talk about Au, that would also have the same value only. So the radius is same, but the mass is more. So what would happen? The density would be more for gold. Mass of gold is greater than mass of silver, right? But the densities are just, but the radiuses are just the same. So density of gold would be more than density of silver. Okay, so that's why this is justified. Now look into the third one, iron, Ag, and Au. Now again, if I draw the structure, okay, iron, you know, this is in 3D, and Ag, mercury, where is it? So let's draw it over here. If we just have a look, the gold, this is where the mercury is. Okay, this is CD, this should be CD. This is where mercury is. But you might be thinking now, mercury is increasing, the radius is increasing over there, right? So but the gold has more value, more mass, okay, and lesser radius. So that's why the gold would be having more density. So that would be it for today. Don't forget to subscribe to my channel.